which tells us to explain the formation of the following molecule. First one is methane, that is CH4. Next we have ammonia, or NH3, and last we have water, H2O. So now we now move on to describe these molecules and explain their formation one by one. So first we take care of the molecule methane, or written as CH4. In order to explain the formation of the methane molecule, first we have to explain the formation of the 4 sp3 hybridized orbital of carbon. So we can say that carbon atom in ground state this can be represented by like this: 2s2, 2px1, 2py1 and 2pz0. So if I am drawing a box model diagram, it will be represented as such. So now there will be a promotion of one 2s electron to the vacant 2pz orbital. So once it is promoted to the vacant 2pz orbital, the carbon atom is in its excited state. In its excited state, the 2s orbital of the carbon and the 3 2p orbitals of the carbon mixes up, or they hybridize among themselves. So we get carbon atom in sp3 hybridized state. So there are 4 sp3 hybridized orbitals that are formed. One, 2, 3 and 4. So this is one sp3, this is another sp3, this is another sp3, and the final sp3 hybridized orbitals. So there are 4 sp3 hybrid orbitals. Now the 4 sp3 hybrid orbitals that are formed will now form 4 sigma bonds with 4 different hydrogen atoms. Each of these 4 sp3 hybrid orbitals which I have drawn contains 1 electron. Like p orbital, each hybrid orbital has 2 lobes, one of which is quite big and the other shrinks down to a negligible size. All the 4 hybrid orbitals being identical, they have the same energy, the same shape, but differ in their orientation in space with respect to each other. The angle between any 2 axes of the sp3 hybrid orbitals are therefore 109 degree 5 minutes. So now, since it forms 4 sigma bonds with 4 different hydrogen atoms, once the carbon atom reaches the sp3 hybridized state, so we can say that the HCH bond angle is equal to 109 degree 5 minutes. That there are 4 sp3 hybrid orbitals of carbon atom in methane. These 4 sp3 hybrid orbitals on the carbon is singly filled, that it is filled up with 1 electrons each. Each of these hybrid orbitals now overlap along the axis with the half-filled 1s orbital on hydrogen atom, and they can form 4 CH sigma bonds. In all the 4 CH bonds that are sigma bonds, the electron density in each bond is symmetrical about the line joining the center of the 2 bonded atoms. Since the CH sigma bond results in the overlap of the sp3 hybrid orbitals of the carbon with the 1s orbital of the hydrogen, it is also designated as sp3 carbon S hydrogen sigma bond, or you can say it S hydrogen sp3 carbon sigma bond. So these are the options that are possible. Now, just like methane, we have already discussed the bond formation in methane. We can also describe the bond formation in ammonia molecule with the help of sp3 hybridization. We can say that in ammonia, the nitrogen atom, like the carbon in methane, undergoes sp3 hybridization. So nitrogen in ground state (2s2), 2px1, 2py1 and 2pz1. So the box model diagram can be written like this. In sp3 hybridized state, or nitrogen atom in this can be written as like this. So there is an overlap between the 2s orbital of the nitrogen and the 3 2p orbitals that are present in the nitrogen, giving rise to formation of 4 sp3 hybridized orbitals. The lone pair remains as it is, and there are 3 more electrons, since their total were 5 electrons to be distributed in 4 orbitals. So this is one sp3 hybridized orbital, this is another, this is one, and this is the final sp3 hybridized orbital. This particular electron pair gives rise to the lone pair of electrons on nitrogen. The hybrid orbital containing the lone pair of electron does not participate in the overlapping or the bond formation process, while the remaining 3 hybrid orbitals being singly filled, the orbitals overlap with the 3 singly filled 1s orbital of those 3 hydrogen that are there, give rise to the formation of the sigma bonds that we have in ammonia. Thus we can say that the sigma bond that are formed in the ammonia can be written as SH sp3n sigma bonds. Now we see that what is the structure of the ammonia molecule that we can draw. We can draw the structure of ammonia molecule like this. So this is actually the structure of the ammonia molecule, known also as the pyramidal structure. The ammonia molecule also is expected to have a tetrahedral shape with the with the HNH bond angles equal to 109 degree 5 minutes. But this is not so. The bond angle or the HNH bond angle that we can see is found to be equal to 107 degree. So there is a sharp degree of decrease in the bond angle in case of ammonia. This is because of the lone pair that we have on the ammonia molecule. The lone pair repels a bond pair more strongly than a bond pair repels another bond pair. So due to this lone pair bond pair repulsion, the angle becomes equal to 107 degree. So there is a decrease in the angle. The molecule gets a little distorted and we call it a trigonal pyramidal shape. So more precisely, we can represent ammonia molecule and say that it has a trigonal pyramidal shape. So after this discussion about the ammonia molecule, we shall now discuss the formation of oxygen, the hybridization of oxygen and the formation of the water molecule. In the formation of the water molecule, the oxygen atom, like the carbon and the nitrogen which we had, gives rise to an sp3 hybridization, and there is a formation of 4 sp3 hybrid orbitals. So how it happens, let us see. So we are discussing the water molecule. In this case, oxygen atom in ground state, it can be represented such 2s2, 2px2, 2py1 and 2pz1. In box model, it can be represented like this. So in sp3 hybridized state, we can say that the 2s orbital overlaps with the 3 2p orbitals that we have, giving rise to the formation of 4 sp3 hybrid orbitals. So there are 4 sp3 hybrid orbitals, and there are a total of 6 electrons to be distributed. So these two gives rise to the formation of 2 lone pair of electrons that we have on the central oxygen atom in the water molecule. So the structure of the water molecule takes a shape like this. So you have oxygen out here, hydrogen, hydrogen. There is one lone pair and there is one lone pair. So these two are the two lone pairs. So water is also expected to have a tetrahedral shape with a bond angle of 109 degree, but this is also not so because of the lone pair repulsion and also the lone pair bond pair repulsion that we have in case of the water molecule. The bond angles becomes 104.5 degrees. So there is a huge decrease in the bond angle from the expected tetrahedral structure. Such a molecule takes the shape of a V shape. So it is also known as a V-shaped molecule. So now we have discussed the formation of methane. We have also discussed the formation of ammonia, and finally we have discussed the formation of the water molecule. So in our next problem solving session, we shall be doing a few more of the board problems that we have and try to solve them and give a probable and a proper answer to each of those questions. So for the time being, it's over from me, and thank you, dear students.